Hello everyone, welcome back to ECE410 Power Electronics. This is lecture 2 or class 2. Today we're going to talk about DC-DC converter. How do you convert one DC level to another DC level and how to do it effectively. Before we get there, we need to understand two elements very important for conversion. One is inductor, another is capacitor. For inductor, if I ask you what is inductor, you have seen inductor in ECE100, also physics 260. Inductor stores energy, right? So it's the energy storage device. We'll call it energy storage device. And stores energy, inductor stores energy in the magnetic field. You have seen that, right? That's inductor. And what is the golden rule of inductors? You know that there's two rules, one for inductor, one for capacitor. Inductor is that the current through an inductor cannot be changed instantaneously. So current through an inductor cannot be changed instantaneously. Right? So current cannot be changed. It takes time to change the current direction through an inductor. See, with these two things, did you see anything wrong with this circuit over here? With this circuit? If you think carefully, you'll see that this inductor over here stores energy, right? So when your switch is on, there's no problem, right? When switch is on, there is no problem. That means you have a complete circuit, so current goes through inductor to the ground. But when switch is off, which switch is off, which switch is off here, that's a problem. So now you remember that inductor stores energy in the magnetic field, and it's going to push current to the same direction until all the energy in the inductive field is reduced to zero. So current going to come this way, right? So that current have no place to go because so it's off. That means when current pushing this way, they're going to store, build up potential over here at this end. So current pushing this way is nowhere to go. So they're going to build potential at this point. That means voltage at this point we're going to build up. So that voltage compared to the ground, if it goes way above this limit of this transistor over here, this transistor could be destroyed. So that's why when switch is off, the inductor pushing current to the same direction that produce a potential here, that build a potential here. That potential buildup could exceed the limit of the transistor and could destroy it. So because of that reason, to release this build-up potential here, we usually use a diode here to go back. So your your current can circulate through this and would not build voltage at this point where your transistor is. So that's one of the remedy for that. We're gonna watch this video in the class so you can see that how it works. All right. And for this circuit over here, it's a capacitor. And again, capacitor also energy storage device. It stores energy in the electric field. Right? And golden rule for the capacitor, voltage across the capacitor cannot be changed instantaneously. Across the capacitor cannot be changed instantaneously. All right. So with that, what will happen over here? If you think if you have the 50 ohm resistors over here, right? If you remove that 50 resistors, what will happen? Think about it. Because of the switching action over here, you're pumping energy from inductor to the capacitor every time you're switching, right? So this inductor will continue to pump energy to the capacitor, and capacitor would not have any other way of releasing this energy So you're gonna store energy and your charge will build up, right? So Q equal to CV, right? So you have a capacity, how much charge a capacitor can hold. So because of its pumping energy continuously to the capacitor, and capacitor doesn't have any other way of dissipating energy, that Q limit for the capacitor could exceed. If that exceed, that capacitor would be destroyed. So that's the reason you need a 50 ohm resistor across the capacitor to discharge the charge. Okay, and also if you don't use the switching circuit, if you don't have the switching circuit over here, if you don't have switching, what does it look like? If you don't have the switching circuit, your input and output would look like this. So R, C, diode, and switching circuit. That means in a DC, if there's no switching here, your inductor will see pure DC. So in DC, inductor becomes a short circuit. All right. And you see the basic circuit over here. So you have an energy source, you have load, and you have the converter made out of these three elements over here. And they have a control circuit. That control circuit will control the switching action of the switch to make sure that you have the appropriate level of voltage conversion from source to the load. And if your switch is lossless, that means at V equal to 0, like when you have a current conducting here which is on, there should not be any voltage drop, so then you're zero power. If is off, then there's no current, also zero power. So the switching should not have any ideal switch should not have any drop, voltage drop or power loss across it. So you would try to solve this converter circuit by using traditional circuit laws like KVL, KCL, nodal analysis. But be careful about that. Every time you're switching, these two switches are changing, you change the circuit. So you have to write down the KVL, KCL every time your switching pattern changes. That is not easy. That's why writing down your KVL, KCL might not work for solving the energy conversion circuit. So how to solve it? Only you can solve it is called conservation of energy. That means we're going to take energy storage device. We'll make sure that we are using energy conservation theory across the device, and you're going to go from there. What is that? Like, for example, if we use inductor for your energy storage device, and if we apply energy conservation law in the inductor should not have any if it's an ideal inductor, should not have any energy stores into the inductor after a period. So whatever energy is stored should be releasing in the next cycle. So there is no energy storage into the inductor for over a period. So how do you apply it? Let's see here. I have a simple circuit over here. So I have two switches, right? Let's say this is 1, right? And this is 2 here. So when 1 is on, it's look like this one here. So 1 on, 2 off, right? And when it's 2 on here, it's look like this, right? So so for this one, if I'm using inductor as an energy storage device, right? So how much energy comes into the inductor when this circuit is one is on? Energy coming from source to the inductor, right? So the energy is power time. So if I know that if let's say switch 1 and 2 that are on and off by 50%, so that means energy coming into the inductor, let's say, is W1, 0 to T over 2, T is the period, right? And then you have voltage in, this input voltage over here, that says voltage input voltage here, and I, the current going through it, right? IL dt, that's the energy came into the inductor during the time when switch 1 is on. And when switch 2 is on here, so then now your inductor release the energy to the capacitor here, right? Or the other output load. So that one would be, let's say, W2, right? So that would be again T over 2 to T, right? So for the latter half of the period, so energy going from inductor to the load, and over here you still, I'm assuming that same current because inductor current cannot be changed instantaneously. So I have now your voltage over here. So your voltage across the inductor, V in, VL, let's and V out here, right? So your VL now would be, let's put VL here, IL dt. So your VL now would be V in minus V out, right? Over here, for this one, your VL over here is same as V in because there is only 2 voltage, right? So V in should be, for this circuit, VL should be V in. For this circuit, VL is V in minus V out, right? So now we can put this together in the equation, and over the time period, if I add these two, there should be 0 because over the period of time, inductor should not have any energy stores in there. So now if I put it back together here, so remember that W1 is 0 to T over 2 VL IL dt, and W2 is this is T over 2 to T over here. That VL, remember the VL would be V in minus V out IL dt. So now if I add them together, W1 plus W2 equal to 0. If I finish integration over here, that would be VL IL T over 2, and over here V in minus V out IL, that should be also T over 2, should be equal to 0, right? So now if I finish the algebra over here, your V out should come into 2 times V in. So this simple circuit, your voltage went up twice in terms of input voltage. Your output voltage is twice of the input voltage. Like if your V in is 12 volts, your V out would be 24 volts. That's the circuit over here. All right. Then in the class we did the 50% D2 ratio, right? We did the 50% D2 ratio for the last one. We're going to do the 25 and 75. Let's see how it works. And also we're going to talk about how the 0% 100% D2 ratio will do. Think about it. We'll see what is the 0% and 100% D2 ratio will do to the circuit. All right. So I'm going to stop here. I'm going to do this one with the generic formula. I will stop here. I'm going to get to this one in next part of the video.